Hello student, let's go to next topic of our syllabus, that is nothing but what? Thermodynamic state variables and equation of state. So thermodynamic state variables little bit we have learned initially also. So first of all what we have done, the thermodynamic variables are the parameters which are get changes in thermodynamic processes that are said to be thermodynamic variables, and there is a it is relation with the equation of state that we know. For ideal gas equation of state is what? PV equal to nRT. So that parameters already we have learned. So just we have to revise it here further. So what should we do? Here the first thing is what? Thermodynamic state variables we have to see. So we know the pressure changes in case of gas, pressure, volume, temperature as well as mass of the gas may get varied or may get changed. So these are considered as the thermodynamic variable, state variables. The pressure, volume, temperature, number of molecules we have taken, number of moles, or we can say mass of the gas. These are the thermodynamic state variables. Now here, every time it is not feasible or it is not possible that the thermodynamic process may not be in equilibrium state, may be in equilibrium state. Some thermodynamic processes are in equilibrium state, some of them may not be in equilibrium state. So one of the best example as they have given in your book, there is a volleyball or football we have taken. If suddenly football get punctured, it is seen that the air inside the ball come outside and it get expand in the environment. In this process, here there is no any parameter, no any state variable is constant. Pressure get changed after puncturing that ball, the pressure inside get changed, volume get changed, temperature may get changed, mass get changed. So this parameter, thermodynamic state variable get changed. So this type of system is said to be non-equilibrium state. This type of system is non-equilibrium system or non-equilibrium state. Apart from this, another example they have mentioned in a book, that is what? When the fuel get burned in automobiles, suppose vehicles, automobile vehicles we have, and the fuel get burned, at that time of burning of the fuel exists in three different stages. Some of them fuel exist in liquid form, some of them is in gaseous form. So various form it is that due to that the pressure get changed, volume get changed of that fluid, or that we can say fuel, volume, pressure get changed. It never become constant, and that is again nothing but what? Non-equilibrium state of the fuel before burning in a automobile. So here in short we can say such a system which is not in equilibrium state, such type of system, that football we have taken when it is punctured or some mixture of the fuel in automobile, such a system which is not in equilibrium cannot be described in terms of state variable. We cannot describe such a system in terms of state variable because the variables are changing, they are not constant. So what should we do? In simple word we can say thermodynamic state variable describe the equilibrium state of system. Whenever we represent thermodynamic state variable, they always represent equilibrium state of system. Okay, it must be in equilibrium, it should not be in non-equilibrium, it must be in equilibrium state. That variable represent the state. Now apart from this, the mathematical relation between this thermodynamic state variable was given in terms of one equation, and that equation of state, that is said to be equation of state, and that we know equation of state is what? PV equal to M into R into T. Pressure, volume, number of mole, gas constant, T is the temperature. So these are the state variables, and their relation was given by this mathematical formula, and that mathematical formula is said to be equation of state. Apart from this, here we can represent the changes in pressure and volume in terms of one graph. We can represent change in pressure and volume in terms of graph. So in this equation PV equal to nRT, if two variables we will consider at a time, so PV equal to nRT, I will write once again, PV equal to nRT, you can write pressure and volume is changing at a time, or pressure and temperature is changing, or volume and temperature is changing. So at a time two parameter can get changed in this system. Now here if we represent out of this same thing, change in pressure and volume, if we represent graphically if we represent volume along x-axis, pressure along y-axis like this, and here we represent the change in the system from point A to some point B, there is change. So this is point B and the change become like this. Now we can represent this as a V2, this as a V1, volume get changed, here it is pressure P2, here it is a pressure P1. So in this fashion we can represent just according to book, we'll go, it is P1, it is P2, it is V1, it is V2. So volume taken along y-axis, pressure taken along x-axis. When system gets changed from point A to point B, there is change in what? Pressure changes. At the same time, volume also gets changed. And such type of graph is said to be PV diagram. Such a diagram is said to be PV diagram. In this PV diagram, what exactly PV diagram means? The changes in the pressure represented corresponding to change in volume in the graphical form, and that is said to be PV diagram, or sometimes it is said to be PV curve, or sometimes it is said to be indicator diagram of system. Indicator diagram of system. So this is the curve, and this curve, when the temperature is constant while doing this study, while change in pressure and volume we are going to study, while doing this, if the temperature is constant, same diagram is said to be isotherm. So when temperature is constant, it is said to be isotherm. Isotherm means temperature remains constant in PV diagram, then that is said to be isotherm. Apart from this, same discussion we have to elongate further in different parameters and different things we have to see. The same discussion we have to elongate. So before going into detail, if you remember, we have derived one equation, change in work done. So that is work done to change the volume from VI to VF, that is dW, if you remember, and that work done equal to what? VI to VF, it is VF. Work done equal force into displacement, so force into further displacement dx we have considered in that case. And if you put the value of force, pressure into area, so you can write this as VI to VF, for pressure into area A into dx. A into dx is nothing but a volume, P into dV. So we can represent VI to VF to change the volume from initial volume to final volume. It is what? P into dV is the work done. So this type of equation already we have derived in your book. In last pedal, so we have seen this derivation of this equation we have learned. In this equation, what exactly dW is? W is the amount of work done required to change the volume of a given system from VI to VF. Change in volume, how much work done is required, that we have calculated here. In this situation, we have to apply the same formula here to the three different cases as discussed in your book. So the first case they have mentioned here, positive work is applied, work is positive with variable pressure, that we have to see. Then negative work with variable pressure, and third one, there is a positive work with a constant pressure. So change in volume is nothing but work that can be done by application of work done. So that we have to learn under this. So this integral in this equation, this integration represent work done. This integration represent work done in changing the volume of gas. The area under PV curve also represent the work done. So we have to represent this integration in terms of work done to expand the gas, to change its volume from VI to VF in terms of PV diagram. We have to represent it. So start with the first. So there are three cases I have told you. Positive work with variable pressure. So let's start with the first diagram here. So here it is the first diagram A. If you see this is a diagram A. Here, if system changes from first point to second point, system changes from 1 to 2, such that at point 1 it has a pressure P1, volume V1, at 2 pressure P2, volume V2. When system changes from 1 to 2, just is going out downward direction. 1 to 2 means what? There is an actual expansion. So suppose the gas we have taken, suppose for this we have to assume some parameter. Let us consider, suppose this is a system. In this system we have taken some gas, just we have seen in last time, and with this it has some such type of pulley, frictionless massless pulleys attached to this, and this is the mixture of the gas we have taken here. Now here we have taken a gas with a mixture, and here massless extensible, that is pulley we have attached to this chamber. Now when this gas can be expanded, either it get expanded, if the gas get expanded, pulley can move to this side. There is expansion of gas. So this is said to be expansion. So it is expansion of gas that can be occurred when this pulley gets shifted outward. If the pulley gets shifted inward, it is what? Compression of gas. When we compress the gas, the pulley gets shifted inward. So that is nothing but a compression of the gas. Second thing, and for these two things we have to learn the PV diagram. When there is expansion of gas, pulley shifted outward. When there's compression of gas, pulley shifted inward. So these two cases we have to learn. Apart from this, the third case we have to see, it can expand at constant pressure. Pressure remains constant, still there would be expansion. How that get occurred in PV diagram, that we have to learn. So start with the first diagram here. So here this is the first diagram. Here there is expansion. Expansion, that means pulley moves outward. So pulley get moved outward, so there is expansion of gas from first to the second parameter with change in pressure as from P1 to P2. Initially pressure at this point is P1, it get decreases to P2. As we come to 2, pressure decreases, it becomes P2. Instead of this, we get this pressure. At the same time, when we move at 1, the volume is V1. When we shifted to 2, volume get increases to V2. So in this process, what get occurred? Pressure decreases, volume increases. Volume increases means what? Change in volume, which correspond to change in pressure. And this area under this curve, this area, it will give the value of this integration. That is amount of work done required to change this. That was given by this area under this curve. And that is nothing but a first diagram for expansion of gas. Let's go to second part. Here, when suppose this pulleys move inward. By moving the pulley inward, what will occur? There is change in volume, decrease in volume with a change in pressure. So here still compression is there. In that situation, let's see. Here compression we are doing. This is expansion because volume increases. Now we have taken part 1 here and 2 here. We are going upward. Initially we are coming downward here. We are coming here like this, coming downward. Now we go in opposite direction. Why we are going opposite direction? Because we are compressing. When we compress the gas, its volume get decreased. So initially volume is V2. Okay, when at 1, volume is V2. When we shift to 1, when we shift from one place to the second stage, 1 to 2, it is seen that volume decreases from V2 to V1. Now we reach to 2. From 1, we reach to 2. Volume decreases from V2 to V1. There is a decrease in volume means what? There is a compression in the gas. At the same time, volume decreases when we move from 1 to 2. Volume decreases, but the pressure increases. Pressure increases from P2 to P1. So it is P1, this is P2. Volume decreases V2 to V1, pressure increases P2 to P1, and that is nothing but this case compression of the gas, and that was done by moving the piston inward the chamber. It will compress. Now this area under this curve will give what? The value of again this integral, which will require work done. The value under this curve give the integration, this integration, that is work done to compress the gas. This is to expand the gas, this is to compress the gas. In both the cases, there is change in pressure. Here P2 to P1, here P1 to P2. Okay. At the third case, here expansion of gas would be there, but there should not be change in pressure. In that case, what they have done, so this is the first position, initial position, this is the final position. As we move from 1 to 2, see, this pressure remains constant, that is P. Pressure remains constant, and that pressure is nothing but a P. And here, while doing this, we are moving from 1 to 2. The volume changes from V1 to V2. Volume get increased. So in this case, there is expansion of the gas, but there is no change in pressure. Pressure remains constant, volume get increases. Now this area under this curve, it will give the value of that integral. That will nothing but what? Amount of work done required to expand the gas without change in pressure. This is amount of work done required. This area gives amount of work done required to compress the gas with change in pressure. Amount of work done required to expand the gas with change in pressure. These are the change in pressure. This is pressure is constant. So this is the thing that thermodynamic state variable and equation of state that we have learned, and these are the 3 parameters for PV diagram that we have learned here. Now apart from this, there is when the volume is constant in any thermodynamic process, if volume is constant, the work done is 0. If there is no change in volume, volume remains constant. If volume can't change, there should not be work done. Work done is required to change the volume. If the volume remains same, the work done required is 0. But there is no displacement, then such type of expansion, this type of changes, and this type of changes we will have to discuss further, and that is said to be free expansion and something. that we'll learn later on. Now let's go to next, thermodynamic processes. What are the thermodynamic processes and how that thermodynamic process works? That part we have to learn. So this parameter we are going to learn again. We have to draw these diagrams again further for next topic. Before that, let's start with this thermodynamic processes. So what the thermodynamic processes are? So thermodynamic processes are the processes in which there is change in parameters that can occur very small amount of change. Infinitesimally small changes get occurred, and that changes are very slow changes occurred in the system, and that type of thermodynamic processes are said to be quasi-static process. Quasi-static process. So these processes are nothing but a processes, thermodynamic processes basically these are, but in this case the changes are occurred very slowly, infinitesimally small. Infinitesimally small means what? The changes occurred, it will take a large amount of time to complete that change. So the process becomes very slow process. Process is slow, changes get occurred, but the changes are very small changes, and to occur that small changes time required is large, and then such type of thermodynamic processes are said to be quasi-static processes, in which the changes get occurred with infinitesimally small changes, slowly small, or you can say very slow changes get occurred, then that process are said to be quasi-static processes. Now we have to go to next topic one, work done during a thermodynamic process. Up till now what we have done, work done to expand the gas, that we have learned initially here. Just I have erased this part. So work done, now we have to see work done during the thermodynamic process. How the work done, whatever we have learned here, three diagrams, same diagrams we have to learn here, work done during thermodynamic processes. So let's start. I have drawn it here, the diagram already, but here how the work done get changes with the path, that is important to learn. So let's start with this work done during a thermodynamic processes. So first of all, work done during a thermodynamic process. Suppose thermodynamic process is going on, how the work done get changes, and what are the parameter on which this work done depends, that we have to find out. So same thing we have done in initial case also by using that equation, W equal to V1 to V2 integration P dV, same thing. So let's start with here. So here this is a PV diagram I have drawn, the first one, this one. Here there are two cases, or we can say two points we have taken. Suppose we want to consider here work done when the process changed from A to B. Suppose this is the point A, this is the point B. When we move from A to B, how the work done is required in this process, thermodynamic process. Initial stage is A, final stage is B. For A, suppose the pressure is Pi and volume is Vi, initial stage. For B, pressure is Pf, volume is Vf. Initially we have taken V1, V2, now here I for initial, F for final stage. So our aim is we have to move the thermodynamic system from A to B. Now we can move from A to B by three methods they have mentioned here. There are three paths they have mentioned. If you remember, just see here the one I have mentioned. This is the first path, A to B. Directly we can move by this path, one path. We can go by second path. First go A to C, then come from C to B. This is second path. And third path they have mentioned, A to D and D to B. Final aim is what? In all these three paths, we start from A, ends at B. We start from A, ends at B. What are changes? Change in path only. Directly from A to B, okay? Or initially A to C, then C to B. Finally come to B. And third one, A to D and D to again B. So these three processes by three paths. When we change the path 1, 2, 3, just what they have done in this topic, they have tried to find out work done in this thermodynamic process. Starting point is A, end point is B. In all these three cases, what they have done, they have calculated the work done required. Work done required for path 1, 2 and 3 they have find out, and finally they have taken some conclusion from this, and that we have to learn today. So let's start with the figure A. Figure A for path 1, we are moving directly from A to B, so this is figure A. So again here, just see, look at here, if you see, this is A and this is the B here. We are coming from A to B in downward direction like this, so we are moving from A to B. Now initial pressure is Pi, final pressure at point B is this nothing but a Pf. Initial volume is Vi, final volume is Vf. So when we move from A to B along the path 1, Then at that time, just we have learned area under this curve. Just I have drawn here shaded region. Area under this curve give the amount of work done required for this change. So what will occur in this case? We move from A to B. Pressure decreases from Pi to Pf. When we move from A to B, pressure decreases from Pi to Pf. At the same time, volume increases from Vi to Vf. Means what? There is an expansion of the gas. There is a expansion of the gas, and this area shaded region under this curve is nothing but a value of integral. Value of integral means what? Work done required to expand this gas along a path 1. For this thermodynamic process, work done required given by this shaded area along a path 1. Let's go to second. That is second path means we go from A to C, then C to B. So this is the diagram. So when we move from A to C, initially A to C, pressure remains constant, but volume get increased from Vi to Vf. Volume get increased from Vi to Vf means there is expansion of gas. Volume increases, expansion with a constant pressure. When we reach to C, when we move from C to B, it is seen that pressure decreases from Pi to Pf, but volume remains constant. So these are the two processes combined, and we pass by the second way, that is second path we pass. So initially A to C we are moving, volume increases, pressure remains constant. C to B we are coming, volume constant, pressure decreases. So that is the thing here. In for this second diagram, in first diagram what get occurred? As we are moving from A to B, at the same time pressure decreases, at the same time volume increases. So both processes are simultaneous here, but here the processes are not simultaneous. Initially pressure is constant, volume increases, then volume is constant, pressure decreases. So both are the example of expansion, but different way the expansion get occur. So this is second diagram. Now when we move from A to C first, A to C, pressure is Pi, it is constant. Volume changes Vi to Vf. Then when we move from C to B, the volume is Vf, pressure decreases from Pi to Pf. And this area under this curve gives the amount of work done required for expansion of this path, part 2. When we follow the part 2, this much amount of work done required for a change in volume, and that is given by area under this curve. And the last one and third part we have to go, and that I have drawn it here below. So if you see this diagram, third diagram here I have drawn. In this case, what get occurred? The third path means what? We have to move from A to D and D to B we have to go. We have to move from A to D. Just look at here. We are here A to D, then D to B. Again here, what get occurred? When we move from A to D, volume remains constant, pressure decreases. Then D to B, pressure remains constant, Pf, but volume increases. So again it is expansion, okay, into different parameter. So let's start with here. When we move from A to D, this point is nothing but D. When we move from A to D, pressure decreases from Pi to Pf, but volume remains constant, Vi. When we move from D to B, toward the final things, D to B, pressure remains constant to Pf, volume increases from Vi to Vf. Now if you see, area under this curve is this much. So this much is the area under curve, and out of this 3 diagram, if you see, area under curve is small for this. So this is the expansion of the gas, where very less amount of area we are getting, so less amount of work done is required for expansion of gas. So minimum work done required is here, that is diagram C, along a path 3. Then the second one is along a path 1, and maximum work done is required for a path 2, that was given by this diagram. So this is nothing but in this fashion we have learned work done required during a thermodynamic processes. And final, it's time to take a conclusion. So finally, at the end of this topic, in your book they have mentioned, we concluded that work done by a system depends only on initial and final condition. Does not depend on initial and final condition. Just I will read once again. We conclude that work done by a system depends not only on initial and final condition, but also depend on intermediate stages, that is, and path along which changes take place. Just a simple thing. work done required does not depend on this directly initial and final condition, because in all these three cases, initial start point is A, end point is B, final point is B. But the paths are different. First path, second path and third path. And it is seen that according to path, work done required during this thermodynamic process changes with the path. Means there are some intermediate stages. On that intermediate stage, this work done depends. Now let's go to next. Heat added during a thermodynamic processes. What get occurred when heat added to thermodynamic processes, that we have to learn now. So for that we have to draw some diagrams here. So I will draw it here. So here let's go to the next topic of the syllabus. The heat added to thermodynamic processes, that already just we have seen the work done during a thermodynamic process. Now how to add heat in thermodynamic processes, that we have to learn. So let's start with the heat added to thermodynamic processes. So to start with this, we have to draw one diagram. So first of all, I will draw it here. The first diagram I will try to draw it here. So this is suppose the chamber in which some gas we have taken, and it has some piston. So suppose this is the piston, part of the piston I will draw it here. So this is the piston, and in this there is some gas molecules are here. This is our system, thermodynamic system, and its first volume is VI. Initial volume of system is VI. Now here we want to add heat added to thermodynamic process, that we have to learn how to add heat. So it's common sense. This type of state 1 we have taken. This is state 1. In your book they have drawn the two diagram. I have drawn it single one. Now suppose we can draw the second one also. So initially, this is the diagram first, initial diagram, where the volume is VI, and this is nothing but what? This is the pulley, frictionless, massless pulley we have considered, and in this gas we have taken, and the gas has a volume, initial volume VI. Now when we heat this gas, when we start heating the gas, if we start heating, it is seen that heating get started. When we start heating, what get occurred? This temperature of gas get increased, and as temperature of gas get increased, gas start expanding. And when gas start expanding, what get occur? This what we have taken a pulley, that pulley gets shifted upward, and as pulley gets shifted upward, there is an expansion of gas. That's it. So in second diagram what they have drawn, so the same diagram they have drawn, little bit modification, just they have increased the volume. So this is the pulley now. So the pulley gets shifted in upward direction like this, and here this is the gas which gets expanded, and it has a final volume that is nothing but a VF, that is expanded. The gas get expand here initially. Before heating it is small, after heating, so this is, we can just, in your book what they have done, they have not shown this candle here, they have shown this heating here, because gas get expanded here, they have shown the expanded gas here. Initially volume is VI. When we heat it, gas get expand, and the pulley get shifted upward, pulley get move upward, and due to moment of the pulley upward, there is change in volume get increased. This is the first method by which we can supply heat to thermodynamic process. How to add the heat? Directly supply the heat by burner or some heating arrangement, heater we can use, directly add the heat to that particular system, thermodynamics. This is the first method to add heat to thermodynamic processes. Now second system they have mentioned, what they have done in second case, second method of adding a heat to thermodynamic process, don't do anything, don't heat it, just enclose that particular whole thing. So what they have done, sudden uncontrolled expansion of gas, that is said to be sudden uncontrolled expansion of gas. What they have taken whole system, and they have divided this system into two parts. System divided into two parts, that is nothing but the first name is X, second name they have given as a Y. And the X part has a volume, it is a closed part, it has a volume VI, and the second part has a volume VF. And this VF and this whole thing is enclosed, it is thermally insulated, we can say. No heat can enter the system, or no heat can go outside the system. Okay, that in this case nothing can go inside, nothing can go outside. So what they have done, whole system is well insulated. So this thing is well insulated, and apart from this, at the top they have kept such type of cap or something, so that there should not be loss of heat into surrounding. Such type of thing is there. So this is the X portion which contains some gas or liquid under study. So that gas is nothing but having a volume VI, and VF, the remaining empty part, which has a volume Vf and nothing is there, no single particle there. They have created vacuum here. So just if you see, they have mentioned here in your book, they have taken here vacuum. So vacuum they was kept in this part Vf. Now what can occur? Whole thing get insulated. After some time, if this border, or we can say the what compartment, they just divide into two compartment X and Y having a volume Vi and Vf, and if we add these two volume together, what we get? To total volume we get. So Vi plus Vi dash, so it should be Vi, it should be Vi dash, and when we add Vi plus Vi dash, it comes to be total final volume Vf. Okay, so after some time, what will occur is surrounded by insulating, but cylinder is kept with surrounded by insulating material. Now, and it has compartment with thin breakable partition. This I have shown here by dark line. It is a partition. It's a very thin partition that can be break. So after some time, it is seen that when partition is suddenly broken, this partition gets suddenly broken, there's an explosion, and due to this explosion, what get occurred? Whatever the gas here, that gets sprayed. When this partition get broken, it gets sprayed throughout this, and once the gas gets sprayed here, it occupies the volume. So volume increases, and that is nothing but sudden expansion of a gas. And this sudden expansion of the gas get occurred, and here sudden expansion of the gas get occurred, and heat get transferred to system here. Due to this sudden expansion, explosion is there, so this layer get broken, this partition get broken, and heat get spread in throughout the chamber, and that is nothing but a second method how to add heat. So nothing we have done, just we have enclosed it. After some time, this layer get broken, and due to that, there is an expansion of the gas. Such type of expansion where we does not push any piston here, it is no need to push any piston because they don't have piston or surface of expansion. Such an expansion is said to be free expansion of the gas, and here in this free expansion also there is change in volume of the gas. Now in this case, finally we can conclude from this, the heat transfer to the system also depends on the path. Heat given to the system is also depends on the path. Here the directly explosion is there. Initially we have to supply the external heat, so depending on that path, to which path we are going to supply the heat. In thermodynamic processes, they conclude the heat transfer to the system also depends on the path. So today we'll stop here. Next video will start with the classification of thermodynamic processes. That is probably last topic of our syllabus, but it is a little bit lengthy. There are 6 processes. Thermodynamic processes are 6 type of: reversible, irreversible, cyclic, and so on. Isochronic, isobaric, that process we have to learn, and then we will stop. Then we'll finish this chapter. But next topic, the heat engines and Carnot cycles, and that part gets skipped this year. Okay, so watch my video. After watching, read the same topic from your book. You will definitely understand the things. Still, if you have the problem, you can contact me. See you in the next day for next video. Thank you.